So now that we have defined our 4 types of neurons that we're going to work with in these live lessons, we need some way to quantify when our neurons are wrong if we're going to figure out how they're going to learn. So the most common way of doing that in machine learning is to use a cost function. So these cost functions quantify the difference between the output that we're getting from a neuron and the output that we would like to have from a neuron. So as throughout these live lessons and in machine learning convention in general, we use the variable y to represent the label, the output that we would like to have. So this could, for example, be a 0 or a 1. And then a is the output of the neuron. So we have z, which we've talked about a lot. We pass that through some kind of function, which could be sigmoid or tanh or ReLU, and then that gives us a. And if the difference between y and a is large, so if the desired value of y is 1, but the a is 0.8, that isn't too bad of a difference. If this was supposed to be a 1 and the value here is 0.2, then that's a larger difference. And when we square that second value, it will be a large cost. And then when we sum that value across all of the samples that we have, all of the labels and samples that we have, we end up with we end up with our total cost across a given sample. The problem with using quadratic cost, which is also known as mean squared error and is very common in linear regression, these kinds of common machine learning applications, is that at low values or very high values of z in our neurons, this learning happens slowly on our networks. And across the tens of thousands or millions of neurons that we have in our networks, that ends up creating an appreciable slowdown in learning. So typically, the cost that we'll use is cross entropy. Now, it has a bit of a complex looking formula. And so we're going to quickly look at a code demo of how this cross entropy works. The bottom line, however, is that this funky looking equation was selected specifically so that when you take the derivative of this to learn with, we'll talk about that in a few minutes, but when you take the derivative, it allows you to learn faster the greater the difference between the true value y and the output from a neuron A. So it's a very clever thing indeed. So let's move on to a quick code demo to show you how cross entropy works. So we've decided that cross entropy is this fast learning cost function within our neural networks. Let's just have a look at how it performs because it's this relatively long equation. So I have a notebook for you called cross entropy cost. And we're just going to quickly recreate that here, where I've defined a function that takes in the true value that we're trying to output from the network y and the value that is being output a. So let's try it when we have a few different values. So if the true value of y is 0 and our output from the neuron is quite close to that, like 0.01, then the cost is quite small. Similarly, if the true value is quite high and the value output is quite high, then cost is also quite a small number. But the larger that the true value gets from the value output, the larger the cost becomes. So we just have a few examples here where 0 is the desired output, but we're not getting that. We're getting these large deviations from 0. Then we see larger costs. So that's how cross entropy works in terms of calculating it. And the key thing to remember is that when we're learning with cross entropy, when we take the derivative of this to learn in our networks, the larger the difference between the true value and the value being output from the neuron, the faster that these neurons learn. So that's a wonderful property. So now we've covered the kinds of neurons that we have. We've covered how we quantify how wrong the outputs from neurons can be. Now we need to know how we can take that information, that wrongness information, and make it right. How can we learn to make the network output values that are closer to the real values? Well, we're going to use gradient descent, which for people familiar with machine learning, you'll have seen this everywhere. So gradient descent is a common approach for figuring out how to learn, how to find the lowest cost possible. So this is a simple one-dimensional example where we only have one parameter. So this could be a weight in a neuron, this could be a bias in a neuron, and the neurons start with random initial values. So we could be anywhere here with any value p. And then from that point, we want to figure out how to step in the direction of the lowest cost, the smallest difference between the true values and the values being output by the neurons. So to do that, we take the derivative of the cross function, and then we can step in the direction of a lower cost. So this is a very simple example with only one parameter that we're trying to tune. You can visually look at this and say, well, obviously you need to be lowering p, but not too low. You don't want to get all the way down here where cost gets high again. But if we get to a value around here, we're going to have the lowest cost possible. Well, that's easy to do by eye when there's only one parameter in your model. But neural networks that we'll be building in these live lessons have millions of parameters, and so there's no chance that you could by eye see how to do this. Therefore, a technique like gradient descent ends up being what you need to use. All right, we're getting there. We're in the home stretch for essential theory here. So we've covered neurons. We've covered how to quantify the wrongness of the output of those neurons. We've figured out how to learn with our neurons. The next thing is how can we efficiently learn through all of the neurons in this network. So in this neural network here, we only have 2 layers, but we could have hundreds of layers potentially. In these live lessons, we'll be building networks with more than a dozen hidden layers. And so we need an incredibly clever way of having gradient descent happen throughout our network, through all of the layers. And luckily, we have it. So there's something called backpropagation, which leverages the chain rule, which you may remember from calculus, and that enables us to almost magically have the network pass some outputs, some guess. It's given some inputs, some sample of x's, and then it's trying to guess what y should be. And wherever it's wrong, we can backpropagate the loss, the cost, via gradient descent through this entire network, figure out how to adjust weights throughout the network, and then we can take another guess with a new set of samples x, and those values pass through the weights and the biases of this neural network. They get to y, and again, wherever we're wrong, we backpropagate that error through the network. We make little changes to the weights and the biases of all these neurons, and we repeat that back and forward, new samples of x. How close was that to y? What was my cost? Backpropagating the error, and by repeating that thousands or millions or billions of times, we start to have weights and biases in our network that are nearly never wrong in some cases, where we can accurately guess the MNIST digits or whatever our samples are very accurately. Alrighty, so this is the very final step of theory, and then we'll get back into some applications. We have our arsenal of powerful neural network options growing here on the right. We have one final thing to talk about here. So this is the output layer. So our hidden layers we've now covered. We've talked about dense, fully connected layers where every neuron in the input connects to a hidden layer, and then every neuron in that first hidden layer connects to every neuron in the second hidden layer. So that's a dense or fully connected layer. We've talked about those. We've applied those in the last lesson. We talked about them at the beginning of this lesson. But now in the output layer, we need some other kind of neuron to describe probabilities. So I have the equation here, but I think I can more easily explain it to you in code. So let's dive into an example here. So I've created for you a little notebook here called softmax. Let's do a quick demo of how the softmax layer works. So let's say we have 3 outputs from a layer. So there's 3 guesses. This network is designed to guess just 3 of the MNIST digits. So it can guess a 0, a 1, or a 2. Let's say the output into this softmax layer, it's guessed that this is a 0, is pretty small. It gives that a -1. It's guessed that this is a 1, is slightly larger. It gives that a value of 1. But it's guessed that this is a 2. It's the one that it's most confident about. It assigns a score of 5. So higher values represent a stronger confidence in class choice. So if we pass these guesses of class into the numerator of the softmax, that's simply taking the exponent. So the exponent of the first one, the guess that this is a 0, is a relatively small number. It's guessed that this is a 1, is a larger number, but it's guessed that this is a 2, is even larger, much, much larger. So we only had these small increments in confidence on the input into the softmax layer. So, -1 through 5 isn't this huge difference, but the values output by the exponent in the numerator of the softmax function are quite a huge difference, from 148 down to 0.36. So critically, taking this exponent puts everything above 0, and it lends great weight to slightly higher values, to the 5 here, for instance. Now, what the denominator of the softmax function does is it's simply saying, well, what is the sum of all these values? So what's the sum of its guess for the 3 classes? And its sum is 151. So then we have kind of a probability. The network is saying, I'm guessing for class 0 that this value, 0.36, or exponent of its guess of class 0 divided by sigma, it's a very small chance. So it's saying, oh, well, there's a less than 1% chance that class 0 is the correct output. But for the highest guessed, for the class 2, it's saying, well, I'm assigning a very high probability, in fact, a 98% probability that the class is 2 of these 3 options. So essentially what the softmax is letting us do is taking any weighting of confidence in some class prediction and giving us a probability score between 0 to 1 for all of those classes. All right, you made it to the end of the essential theory. So now we're well positioned to be building some even more powerful neural networks going forward. So we know what kinds of neurons we can have, and we understand how they function, how they take inputs and create outputs. We understand how to quantify how right or how wrong the outputs from those neurons are. We know that we have gradient descent to learn how to decrease the wrongness of our neurons. We know how we can use backpropagation to learn how to learn through the entire network, no matter how deep it is. And then we also we've added to our arsenal of layers the softmax probability output layer on top of the dense layer that we'd already gone over earlier. So we're all set. Let's move on.